This is an introduction to the Frobenius method for linear ordinary differential equations. It assumes that you know about power series and basic facts about linear ordinary differential equations. It doesn't include a worked example. There is another video in this series which is an example of the Frobenius method worked in detail. Well, here's the type of differential equation that we're talking about. It's a second-order linear homogeneous equation, and it's got no coefficient in front of the u double dashed. And if you have a differential equation where there is a coefficient in front of the u double dashed, you can always get rid of it by just dividing the whole equation through by it. We'll see an example of that in a minute. The whole idea of the method is to expand in a series about points where one of the coefficient functions is singular. So we need a couple of definitions. A regular point of this differential equation is a point where p and q are both analytic. That means both those functions are continuous, can be differentiated any number of times at that point, and equal their Taylor series about that point. And pretty obviously, a singular point is a point that's not regular. In other words, either p or q or both have a singularity at that point. Now, there's a especially simple type of singular point, a regular singular point, and that's one where if the point is called z0, then the functions z minus z0 p of z and z minus z0 squared q of z are both analytic at the point z0, which is the singular point. In the language of complex variables, you can say p has a singularity which is no worse than a pole at z0, and q has a singularity that's no worse than a double pole at z0. So let's look at an example. This differential equation here can be expressed in this standard form here just by dividing both sides by 1 minus x squared. So you get this equation here. You might, by the way, recognize this differential equation as Legendre's equation, but if you don't recognize it, it doesn't matter. You see that 0 is a regular point because neither of these coefficients 2x over 1 minus x squared or this one here, neither of those coefficients are singular at x equals 0. But at x equals plus or minus 1, they are singular, and if you use this test here, it's easy to see that 1 and minus 1 are both regular singular points for this differential equation. And now here's another example. And if you look at this equation, I mean, we start out with it with a coefficient z cubed in front of u double dashed. We divide through by it and get this equation there. If you look at the coefficient of u, this is the function q in the notation that we're using here. This is z to the minus 3. That's got a singularity at 0, and if so z0 in this notation here is 0. So if you multiply this by z squared, you get something which is not analytic. It's still got a 1 over z singularity. So 0 is an irregular singular point for the equation in example 2. Now, let's think about how functions behave in the neighborhood of a regular point. Then, near a regular point, there are no singularities. You would expect the solution of the differential equation to be continuous and have no singularities. So that means that the function which satisfies the equation, you can expect to behave like z minus a to the k in the neighborhood of a regular point, where k is an integer greater than or equal to 0. In fact, if the function is non-zero, if the solution is non-zero at the point A, then the solution is approximately constant near A, and that's the case where k equals 0, the solution behaves like a constant. If the function that satisfies the equation has a simple 0 at A, then it behaves like z minus a to the power 1 in the neighbourhood of the point A, and if it's got a double 0, then it behaves like z minus a all squared, etc. But in all cases, it is some power of z minus a. But near a singular point, we'd expect a solution to be singular, and the simplest type of singularity is a function like this. It's also a power very similar to this here, but with a non-integer power, lambda. So that's the simplest type of singular function. So we're going to look for a solution in the form that type of singularity times some analytic function f. So this is the type of solution that we're going to be looking for. And if we expand f in a Taylor series about a, we can write this as z minus a to the lambda, that's that term, times f of z, which can be expanded in its Taylor series about the point A, because f is analytic at A. Now, in that series, we can always arrange that the first term, the C0 term, is non-zero. And here's why. Suppose it's 0, then we can write the series in this form here, where the sum runs from 1 to infinity, because we're assuming temporarily that C0 is 0. Then, writing this out without the summation sign, it looks like this, and this is now z minus a to some power times a power series with a non-zero constant term. Unless C1 is 0, and if C1 is 0, you use the same dodge again to get this expressed as z minus a to the lambda plus 2 times C2 plus C3 times z minus a, etc. So, to cut a long story short, we can always arrange by choosing lambda appropriately that the first term of the power series is non-zero. And that is quite essential for the Frobenius method to work, as we'll see soon. So we call a series of this type a Frobenius series, and that's the definition of a Frobenius series. It's just what we've been talking about. And a beautiful theorem of Fuchs says that if A is a regular singular point, then there is guaranteed to be at least one solution in the form of a Frobenius series about A, and it converges inside a disk whose radius is the distance from A to the nearest other singular point. So the idea is, if this is a singular point, and if that is some other singularity, then the Frobenius series converges about inside a disk like that. It is the largest disk which doesn't include the other nearest singularity inside it. Now, how do we find the power lambda and the coefficients in a Frobenius solution? Well, first, before answering that, we make a technical improvement. We simplify the form of the Frobenius series by changing variables. If the singularity is at A, we define a new variable z dashed equal to z minus a, and then you see z dashed is 0 at the singularity, so z dashed is a more convenient variable. So change variables, transform the differential equation, that will change the form of the differential equation, and then just drop the dashes on the z, and you get a new differential equation and a new form of the Frobenius series that looks like that. And now we substitute the series into the differential equation. What you get will always be an equation of very much the same form, a series of very much the same form equal to 0, it equals 0 for all z, just because the differential equation holds for all z. And the reason you get still a combination of powers of the type z to the lambda plus n for all n is that when you differentiate z to the lambda plus n, when you differentiate, in other words, that z to the lambda plus n becomes z to the lambda plus n minus 1 after one differentiation, and the second derivative is proportional to z to the lambda plus n minus 2. So you still get powers of exactly the same form. Now, a series like this, a combination of different powers of z can equal 0 for all values of z only if each coefficient of a power of z is equal to 0. So to determine the unknown power lambda and the unknown coefficient Cn, what we do is to equate all the coefficients of all the various powers of z to 0. And we start with the lowest power, and when we equate the coefficient of the lowest power to 0, and we use the fact that C0 is not equal to 0, what we get is a quadratic equation for lambda. That may not be obvious. All I'll say is that if you look at an example, you will see why it is that you get a quadratic equation for lambda out of equating the coefficient of the lowest power to 0. And that quadratic equation is called the indicial equation for this differential equation and that singular point. It's called the indicial equation because it determines the index or power lambda that multiplies the power series in the Frobenius form. So we've dealt with the lowest power. Now equate the coefficient of the general term to 0. And what you get is a recurrence relation for the coefficient Cn. And a recurrence relation is an equation that expresses Cn in terms of lower order coefficients. So it might express Cn in terms of Cn minus 1 or Cn minus 2. And the point about that is that it enables you to find all the coefficients just from the first one or two coefficients using the recurrence relation. And notice that the relation contains the index lambda. Now, because the recurrence relation contains lambda, then what you do is you take the indicial equation for lambda, this quadratic equation for lambda, you find the roots, you take one root of the indicial equation, plug it into the recurrence relation, and theory guarantees that if you're talking about a regular singularity, then for at least one value of lambda, the recurrence relation can be solved, giving all the coefficients Cn in terms of the first coefficient Cn. So at a regular singularity, we're in good shape. We are guaranteed to be able to solve and find at least one Frobenius solution in detail. So let's summarize where we've got to. If there is a regular singular point, then there is always a Frobenius solution. Or we can write it in the form z to the lambda times an analytic function phi. Now, suppose the indicial equation has got two roots, lambda 1 and lambda 2. You would expect to get two Frobenius solutions, one for each of the two values of lambda, so that the general solution of the differential equation is a combination of those two Frobenius solutions. Well, that happens sometimes, and it's guaranteed to happen in the case where the difference between the roots is not an integer. So that's the simple case. And things are a bit more complicated if the difference between the roots is an integer. We're going to define lambda 1 to be the larger of the two roots, so that lambda 1 minus lambda 2 is always positive. Then if it's a positive integer, there is always a Frobenius solution using the larger of the two roots, lambda 1. And there might be a second Frobenius solution using the root lambda 2 of the indicial equation, or there might not be a second Frobenius solution, and the second solution in that case turns out to be of this form. It's got a logarithmic singularity, and it's log z times the first Frobenius solution, the one got from lambda 1, plus a second term, which is z to the lambda 2 times some function phi 2, which is analytic at the origin. So there is just one more case to consider, and that's where the indicial equation has only got one root, or in other words, it's got a double root lambda. Then, by Fuchs's theorem, there is always a Frobenius solution, U1, obtained from the Frobenius technique using lambda. And the second solution of the differential equation in this case is of a form very similar to what we had here. So it's got a logarithmic singularity. So when there is a double root of the indicial equation, there's one Frobenius solution and a second solution with a logarithmic singularity at 0. So now you've got a complete catalogue in front of you of the different types of solution that you might have in the neighbourhood of a regular singular point. And finally, I'm going to talk about other ways of writing the solutions. These solutions can be written in various different ways. And for example, this function phi, we've introduced functions phi of z, which are analytic at 0. They can therefore be written as a power series. Every analytic function, by definition, equals its own power series, its own Taylor series, Cn z to the n, from 0 to infinity. And you'll sometimes see solutions written out using that notation instead of the phi notation. But here's a more significantly different way of writing out the solution in the case when lambda 1 minus lambda 2 is an integer. And remember, we said in that case the second solution might be a Frobenius solution, or it might be a solution containing a log. Sometimes you'll see the solution written out in this form as just a single formula with a new arbitrary constant c. So the obvious question is, how does that form of solution relate to the form on the previous page? Well, suppose that c is 0. If c is 0, that whole term disappears, and this second solution is just a Frobenius solution using lambda 2. On the other hand, if c is not equal to 0, then we can take this equation here, or this formula there, I should say, divide it by c, and what you're left with is just u1 log z plus z to the lambda 2 phi 2 of z, which is the second of the forms that we had on the previous page. So the two forms really are equivalent. Most textbooks that I have seen use this form here with the constant c. Personally, I think that c is a kind of spurious constant. It really stands for something that's either 0 or non-zero. And to me, it seems more straightforward to write the solution as an either Frobenius or logarithmic solution, as I've done on the previous page.